Welcome back, folks. When all your friends are teachers and a lot of you are recording videos over the summer, sometimes you place a bet. Sometimes you lose the bet. I'm not telling you what the bet was, but here we are. I'm not going to make it through the whole video like this. Maximum power transfer theorem. I wanted to give you another example. You're going to see it asked in a different way sometimes, and I'm hoping that in looking at this circuit, it's simpler than the last example that we looked at. But the question's asked in a different way. I'm going to use a Thevenin equivalent instead of a Norton because they both work. I'm hoping in asking it in this way that it's going to help you conceptually understand the implications of maximum power transfer theorem. Okay, so let's get that example. And there it is. So nice and simple circuit. I think we've had enough of that. Don't touch your face. Okay. You think this filters? Is it an N95 nose? I don't know. Anyhow. Okay, so there you go. Paid up on my bet. Anyhow, so here's a circuit. Can RL dissipate 50 watts in this circuit? So RL is drawn over here, and we don't know what its maximum power is. We know it's not going to be when it's 0 ohms. We know when it's not going to be when it's infinite ohms. It's going to be somewhere in the middle, and we're going to go find that. Once we find that, we can figure out what its maximum power is, and that's going to tell us whether or not it can actually dissipate 50 watts. So the answer is a yes, no, right? You can just flip a coin and say like, yeah, yes or no. We got a 50-50 shot of being right, but we'd like to have something to back up our answer. And the thing we're going to use to back up our answer is a Thevenin equivalent circuit and the maximum power transfer theorem. So let's go find the Thevenin equivalent as quick as we can. So let me make a copy here, and let's use this to go find V Thevenin. Okay, we remove the load since it's drawn, and we find the voltage, the open circuit voltage, which is equal to V Thevenin, where that load was connected. So if you look at this circuit really quickly, you can do the analysis any way you want. There's only one mesh. You could go use mesh. You can do the shortcut and things like that. But V open circuit is really the voltage across R2. And now these two are in series since I removed that load. So it's really a voltage divider. The clowns got loose upstairs too. We'll see if the sound suppression filters that out. Okay, so the open circuit is really, we can find it with the voltage divider. Okay, so let's see, 32 volts. We want to know the voltage across the 12 ohm, and the 12 ohm is in series with the 4 ohm. Okay, so let's find the open circuit that way. Since we know and love the voltage divider times 32. And it's 24 volts. Okay, 24 volts. All right, using the same circuit, so I got another copy of it down here. Let's go find R Thevenin. And I'm most definitely going to use method 1 in this one because it's so nice and simple. Okay, so take the independent supplies, replace them by their ideal resistances, a short in that case, and we're going to find our Thevenin looking back into the circuit from this side. All right, 4 is in parallel with 12 in this case. I'm pretty certain that's 3. But I don't trust my brain. It's 3. I should have trusted my brain. Okay, so that's 3 ohms. All right, so with that information, I've got 24 volts for V Thevenin. I've got 3 ohms for R Thevenin. We can draw the equivalent supply. Okay, and this is 24 volts. Because that's V Thevenin. Here's R Thevenin. And then if we want to maximize the load, we can maximize the power dissipated by the load. We can connect that here just like we would connect it to the original circuit because this is an equivalent circuit. So this is our 3 ohms here. And if we want to maximize it, we make that 3 ohms as well. Okay, so now I got to go find what the power is here. So the power dissipated by the load is going to be the voltage across the load, and I'm going to use the other form because it's going to be kind of similarly easy to find as the directly previous example. Okay, this one I'm finding the voltage because I have a voltage divider and I have 2 equal resistances, so it's again going to be half. Okay, so this is going to be 12 volts. That's half of 24. I'm going to square that, so that's going to end up being 144, and I'm dividing by 3. 144 divided by 3, that's actually divisible by 3. Uh-oh. 144 divided by 3, 48. I would have gotten that right too. Okay, so now we get 48 watts. But that's not our answer. You got to look at the original question. Hopefully you're looking at the image along with me. I'm going to scroll up here. Can RL dissipate 50 watts in this circuit? Well, 50 watts is greater than 48 watts, and 48 watts is the maximum. Okay, so if we think back to when I plotted it, when I first introduced maximum power transfer theorem, the plot looked like this, right? And I'm saying this peak is 48 watts, and we want to dissipate 50 watts up here. It's not going to happen. Okay, so the answer is no. Okay, RL, we'll make it into a complete sentence just to make those English teachers happy, like their jobs weren't a waste. Cannot dissipate. They really weren't, if you ask me, but 50 watts. RL cannot dissipate 50 watts. You learn critical thinking over there. Now, and then we apply it to engineering here. Okay, so that's another take on the maximum power transfer theorem. There's your answer. And I think it's one of our simpler theorems. We're going to continue to abuse Thevenin's and Norton's. I'm going to teach you an impractical way to simplify or to solve circuits, but it is a very practical way to simplify circuits if your analysis is a little bit too complex. So that's coming up next. No more clown noses, I promise. Stay tuned and good luck.